So in this video, we'll take a little bit of time to discuss the principal values of the inverse trig functions, why they arise, why they are what they are, and hopefully put some sense to what the calculator does when we type in inverse sine of such and such or inverse tangent of whatever. So basically the principal values are the restricted ranges of the answers we would get when we evaluate inverse sine of 1/2, inverse cosine of negative 0.6. The calculator is always going to return values that are within set ranges for inverse trig evaluations. We want to make sure we recognize that and realize what the calculator is going to do when we type in inverse sine, inverse cosine, inverse tangent of whatever. So the principal values are the only values the calculators are going to produce. The restriction is going to be arrived at by checking out the normal trigonometric functions. So we're about to click ahead and look at some graphs of sine, cosine, and tangent and try to see if we can use those graphs along with a little bit of help from the unit circle to try to figure out what the principal values would be for inverse sine, inverse cosine, and inverse tangent. So this last statement here is kind of wordy, kind of lengthy, kind of weird. Hopefully we'll be able to make some sense out of that once we click ahead and start looking at the graphs. But the way that we determine these principal values is we look at the smallest set of angles. And we have to make sure that the set of angles we look at includes 0. So the smallest set of angles, including angle 0, that the sine, cosine, and tangent functions would go through that produce every single one of their possible outputs. Kind of weird to see it in writing, hear me say it. We'll try to make sure we recognize what that means by looking at this screen. So on this screen, what you see is you see a graph of sine of x, cosine of x, and tangent of x. I'm going to focus on the sine graph first off. So if you look at the sine graph, we've got the red graph here, so it definitely looks like the sine wave. We don't see the full sine wave here, just a stretch of it, and I have the stretch that includes 0. So can we identify the smallest set of angles that includes the angle 0 that the sine wave takes to produce every one of its outputs? So if I start at 0 and start progressing through these positive angles, I'm getting up to the value of positive 1, I come back down to 0, but I still need to produce all the negative values that sine of x takes on. So I would have to extend outward to here till my sine function reaches a value of -1 in order to produce every possible output of that sine wave. That's actually not the smallest possible set of values that includes 0 that it takes to produce every output of the sine function. If I look at going from this point down here, where sine is equal to -1, to this point up here, where sine is equal to +1, hopefully you can convince yourself that this stretch of the sine wave produces every possible output of the sine function, and that stretch is a little shorter across the x-axis than what I had here going from 0 outward to that spot where I left off. So I'm going to get rid of some of this highlighting, and we'll highlight the principal values for the inverse sine function. The inverse sine function is always going to return a value between -π/2 and π/2. So when you evaluate inverse sine, you're always going to get an angle that comes from this stretch of the unit circle, somewhere between -π/2 and +π/2. Now if you look at the cosine function is a little nicer to handle. So we've got the blue graph here. The blue graph at the angle of 0 starts at +1. If I just extend outward across the positive portion of the graph, if I go to here, I've gone from +1 down to -1. I've produced all possible values. I wouldn't have a situation this time around where I'd come over here and extend back this way, because if I start at -π/2 like I had to for the sine function, I'm going to have to still extend out to pi to get every possible value, because I don't take on any of the negative values till I cross this x-intercept here and dip below. So the set of principal values for inverse cosine range from 0 to pi. So anytime you type in inverse cosine of such and such to the calculator, your calculator will always return an angle that's in between 0 and pi radians. The last function that we see here, the inverse tangent function, we have the angle 0 right here. If I go down to this stretch of the graph and just kind of come up, I produce every possible value, all of the negatives as well as all of the positive values that tangent takes on if I let my inputs range from negative pi by 2 to pi by 2. So the only difference between the restricted values for inverse tangent and inverse sine is that inverse sine is going to be defined at negative pi by 2 and pi by 2, but inverse tangent has an asymptote at those spots, so it's not. So the principal values for each of the inverse trig functions are listed here. Inverse sine is always going to return a value when you evaluate it on the calculator between negative pi by 2 and pi by 2. Inverse cosine always between 0 and pi. In the brackets denote that we're including the endpoints. We just said a few seconds ago why we're not including the negative pi by 2 or the pi by 2 for inverse tangent. Tangent function's undefined at those locations. We have asymptotes there. Therefore, we don't ever get an answer of negative pi by 2 or pi by 2 for inverse tangent. So you hit the button on the calculator, inverse sine. Answer's always between these angles, inverse cosine always between these, and inverse tangent always between these. Those are the smallest sets of angles that each of the normal trig functions take. That includes the angle 0 to produce all of their possible outputs.